synthesis of some heterocyclic compounds. Especially in this class, we are discussing the synthesis of pyrrole and also furan. In the next class, we will study the synthesis of pyridine, which is usually asked for 5 marks. So here we will have some 2 marks questions, very small preparations. So we'll see the synthesis of first furan from 1,4-diketones. 1,4-diketones. We have many types of preparation for this furan and also pyrrole, but this 1,4-diketones, from 1,4-diketones, which has been asked many times, so that's why we'll just restrict it to the preparation of furan and pyrrole from the 1,4-diketones. So just for your reference, 1,4-diketones, yeah, here you see with respect to first position and fourth position, if I put 1, 2, 3, 4, at first and fourth or first position and fourth position we have ketonic groups. So these compounds are known as 1,4-diketones, and these are also showing some transformations. So they are dynamically equilibrium with tautomerism, that is showing keto-enol tautomerism. So this ketone group can be converted into enol, so that's why they show some keto-enol tautomerism. So when this occurs, so one of the hydrogen from here will donate electron and that shift to the oxygen, it gets the O minus and this H attacks here. Here the same thing, one of the H will give electron and it electron shift to the oxygen, it becomes O minus and H attacks here. So this will become OH, this will become OH, these two will become double bonds. See here, CH, CH, double bond, COH, R, COH, R. Okay, these are known as same compound, 1,4-diketone, but it is in the ketonic form, and this is in the enolic form. Enolic form. It has double bond ene and alcohol groups ol. Enolic form. So this enolic form is very important for the preparation of diketones. So if you take that enolic form of 1,4-diketone, yes, this is 1,4-diketone. This is in the enolic form. Which usually undergoes dehydration. Okay, when it undergoes dehydration, obviously dehydration by heating in presence of phosphorus pentoxide or even sulfuric acid, concentrated sulfuric acid, it undergoes dehydration. Here water molecule will be released. So one of the AH and OH will release. So now it becomes CH, CH, double bond C, double bond C, R, R, this become O. This is nothing but a derivative of phenol. So it is 1,4-dialkyl. Now we can say 1,4-dialkyl furan. 1,4-dialkyl furan can be prepared. This is a very simple method that usually asks for 2 marks in your exam. But if you want to synthesize pure furan. So here no, we do not need any alkyl derivative. Then we have to replace this R with H. CH double bond, sorry, CH double bond C double bond C H H. This is OH OH. This is nothing but succinaldehyde. This is succinaldehyde. Succinaldehyde. But it is in enolic form. It is in enolic form. Please remember, sir, you can say, you can ask me like there is no aldehyde, sorry, ketonic group or aldehyde group, sir, but you are writing, actually there are alcohol group, but you are writing aldehyde. Actually it is aldehyde, but it is in the form of enolic. It will be like this. Okay, here if you replace with R by H, that is a succinaldehyde. So this succinaldehyde also, when it undergoes dehydration, okay, so here we can take a temperature around 160 degrees centigrade. It undergoes complete dehydration. Same in presence of phosphorus pentoxide or sulfuric acid. Here also dehydration takes place and it gives us furan. CH single bond CH double bond C double bond C O O. This is our furan. We can get the furan directly from succinaldehyde. Succinaldehyde by the dehydration in presence of phosphorus pentoxide. This is a very simple method which you usually ask for 2 marks in your exam. Okay, I think you will get it. So if you take general diketone, 1,4-diketone, you will get a alkyl derivative of furan. And if you take a succinaldehyde, an example of 1,4-diketone, then you will get the furan as the product. So you can write from here the synthesis. Okay, so this is what happens before the reaction. I am just representing over here. So this is very, it is always in dynamically equilibrium. If you find this ketonic form, it will be enolic form. Both are always in dynamic, both are 1,4-diketones. They are not two compounds. Sorry, not both, they are not two compounds. This is only one compound that present in both the states, physical states. That is isomerism. Thiophene can also be synthesized from 1,4-diketone in the same way as furan has been synthesized. So here, same 1,4-diketone, okay, as you know, it undergoes keto-enol tautomerism. So this enolic form, okay, this is a 1,4-diketone in its enolic form. This is in ketonic form. So the same compound, if it dehydrates, when it undergoes dehydration with phosphorus pentoxide, then it gives us furan derivative. If it undergoes same dehydration instead of phosphorus pentoxide, here I am going to take a phosphorus pentasulfide. Phosphorus pentasulfide. If you have oxygen, if you need oxygen, we will take oxygen. If you need sulfur, then we will take sulfur. Phosphorus pentasulfide. Phosphorus pentasulfide. Okay. In presence of phosphorus pentasulfide, this 1,4-diketone undergoes dehydration and it gives us the thiophene. Thiophene derivative. So it is the thiophene derivative. As usual, at first and fourth position we have disulfide. That's why it is alkyl groups. So it is 1,4-dialkyl thiophene. As usual, if you want pure thiophene, then we have to take, instead of this general compound, we have to take a specific compound, that is CH double bond C, here H OH. This is succinic dialdehyde. Sorry, in the furan I have written succinic aldehyde. It was succinic dialdehyde. Please make correction yourself. So succinic dialdehyde, the same compound, when it undergoes dehydration in presence of phosphorus pentasulfide, so it will be, I think, it just need 100 degrees centigrade. So here now we will get the thiophene as a product. We got the thiophene. So same furan and thiophene can be synthesized, this 1,4-diketone from 1,4-diketone. The only you have to replace the dehydrating reagent, and here we will take phosphorus pentasulfide. In the case of furan, we have taken phosphorus pentoxide. So this is about the synthesis of thiophene from 1,4-diketones. In the same way how furan and thiophene could able to synthesize from 1,4-diketone, the pyrrole also can be synthesized from 1,4-diketone. So let us see that. So this is 1,4-diketone. It is in ketonic form. As you already know that it is showing keto-enol tautomerism. It is dynamically present in another form or another isomer, the same compound, that is the enolic form. This is the enolic form of 1,4-diketone. One comma 4 diketone. The same way here also it undergoes dehydration, along with it is treating with ammonia. Okay, it undergoes dehydration, and also in presence of ammonia it gives us the derivative of pyrrole. This is pyrrole. So it is, as usual, one at first and fourth position we have alkyl groups. So it is also 1,4 dialkyl pyrrole. 1,4 dialkyl pyrrole. The same way, if you need to prepare the pure pyrrole compound, we again have to take the succinic dialdehyde. This is succinic dialdehyde. It is in the enolic form. enolic form. So it undergoes dehydration about 130 degrees centigrade, and it is treated with ammonia, will give us pyrrole. Will give us pyrrole. Will give us pyrrole. So using succinic dialdehyde, an example of 1,4-diketone, when it undergoes dehydration and treated with ammonia, will give us pyrrole. So these three compounds, thiophene, furan, and also this pyrrole, can be synthesized from 1,4-diketones, one of which may be asked in your exam for 2 marks. This is a very simple and important method for the preparation of these 5-membered heterocyclic rings. This is also industrially applicable and industrially used, employed method for the preparation of 1,4-diketones. Thank you. Thank you for watching my video. Please like it and share with your friends, please, and subscribe my channel. Thank you. Hi students, today we are going to see the preparation of pyridine derivatives. So here it is from the hand synthesis of pyridine derivatives. In the last class we have seen the synthesis of pyrrole, furan and thiophene from 1,4-diketones. So here we'll see the hand synthesis for the pyridine derivatives. So I have written the statement of this synthesis on the board. That is the condensation of a beta keto ester with an aldehyde and ammonia, and it produces a dihydropyridine derivative, which on further oxidation with nitric acid will produce a nitro derivative. Sorry, we will produce a pyridine derivative. We'll see this reaction, and it is one of the very important question for your exam. So those the preparation of those 3 5-membered heterocyclic rings from 1,4-diketones will ask in for 2 marks. So this question usually asks for 4 or 5 marks. So we also have a small mechanism of this reaction also we are going to discuss in this chapter. Usually for preparations we do not need to write the mechanism, but many of the times this question has also used to be asked for 5 marks. So that's why we'll also discuss the mechanism of the reaction. So I'm going to take, here we are taking 2 moles of beta keto esters, 2 molecules, and one aldehyde and ammonia. See here, CH3, CO, CH2, CO, OC2, H5. So it is one of the beta keto ester. So this is COOR. Okay, COOR. This is ethyl group. This is an ester group. This is an ester group, and alpha position. This is beta position. At beta position we have a ketonic group. So this is an example of an beta keto ester. Beta keto ester. You already know the name of this compound because it has come in your enolates chapter. So this is EAA, ethyl acetoacetate. Ethyl acetoacetate. EAA. It is one of the very good reagent for most of the organic synthesis. This EAA and DEM, diethyl malonate, those 2 compounds you have studied in the synthesis via enolates method. So yeah, this is an example of beta keto ester. It is, here we have taken 2 molecules. It is going to react with an aldehyde. Let me take the aldehyde CH3 COH. This is acetaldehyde. Okay, and ammonia, NH3. So all these three will get condensed and it is going to give us a dihydropyridine derivative, ammonia. Okay, dihydro. So usually condensation means by heating. Condensation means heating with removal of water, that we'll see in the mechanism. So here, yeah, so nitrogen, CH3, CH3, COO, C2H5, and ester. Here also COO, C2H5, and ester group. Here also CH3 and double bond H. So this is a dihydropyridine derivative. Dihydropyridine derivative. So why it is called dihydropyridine? Because in the case of pyridine, usually there is no hydrogen, but here is an extra hydrogen. Here also one extra hydrogen. So there are two hydrogens. We have to remove this hydrogen, and that will be done by the oxidation actually. So that's why it has having a two extra hydrogens in the pyridine. It also, that's why it is dihydropyridine molecule. So as usual, which further undergo oxidation with HNO3. Okay, it is undergoing oxidation. So now it will produce a pyridine derivative. So here removal of H2, dehydrogenation. Dehydrogenation is also known as oxidation. So removing this hydrogen and this hydrogen will give us a pyridine derivative. So this will be the pyridine derivative. CH3. Okay, this is the pyridine derivative. So now you can see the complete pyridine cycle ring. Okay, pyridine derivative. Okay, so pyridine derivative. This process is given by the Hans, German chemist. So you can remove all this ester group also by hydrolysis and decarboxylation. So those also can be removed. So usually this hydrolysis and decarboxylation will be done when we treat with base and calcium oxide. These are good reagents. Okay, for hydrolysis, basic hydrolysis with decarboxylation by heating. So here we are going to form CH3, CH3, CH3. Yeah, an alkyl derivative of pyridine. Alkyl derivative of pyridine. Okay, this is we can get from this hand synthesis. If you name this one 2, 4, 6. Okay, at second position, 4th position, and 6th position we have a methyl group. So then it is 2, 4, 6 trimethyl pyridine. So this much we can get from the hand synthesis. So no direct formation of the pyridine. It will first form a dihydropyridine, and on oxidation it will forming a pyridine derivatives. So it is one of the very important method we have in our syllabus for 4 marks or 5 marks. Okay, so it's very simple. 2 moles of EAA, beta ketoester, will condense with aldehyde and ammonia, forming first dihydropyridine derivative, which upon oxidation give pyridine derivative. So this is also pyridine derivative. So here we have removed just that ester groups by hydrolysis and decarboxylation. Okay. Yes. Many times its mechanism has been asked. So now let us see the mechanism of this synthesis. If you see the mechanism of this reaction as the synthesis, hence synthesis of pyridine derivatives, we can make it in 3 steps. So let me write the first step, where this beta ketoester condense with the ammonia. Okay, so here CH3, this is EAA. Okay, so this is a ketonic group. So by the internal proton transfer, this ketonic group can be converted into the enolic form, which is an isomer of this same compound, that is ketoenol tautomerism. So by ketoenol tautomerism, this aldehydic group, sorry, this ketonic group will convert into an enolic group. So then it will become CH3 COH. This become double bond now. CH CO COC2H5. Okay, this is the same EAA, but it is in enolic form. Same EAA, it is in ketonic form. Ketonic form. Okay, so this enolic form, when it is treated or condensed with ammonia, usually ketones when react with ammonia, the condensation product will be the imines. So here let's just substitute, so then it will be easier for us to understand. Okay, here this ammonia will be NH2 minus and H plus. Okay, this is usually NH2 minus and H plus. This just I'm just replacing this NH2 minus, and OH minus will be replaced by this NH2 minus, and here this OH minus and this H plus will be eliminating as water. That is also a condensation. So by eliminating water, I'm going to get CH3 C NH2 double bond CH CO OC2H5. Okay, just it's like a substitution, but it is actually a condensation. We have removed water, and I just made it easier for you to understand. So that's why enolic form of the EAA has been taken. Okay, yeah, this is, let me call this as EA. Okay, and in the second step, okay, this EAA molecule will be condensed with aldehyde. Okay, we have taken an example of acetaldehyde, CH3 COH, acetaldehyde. Now it is going to condense with this EAA. CO CH3, see, CH3CO CH2 CO OC2H5. Okay, this is also same compound, EAA. So when these compounds both under condensation, so here this oxygen and H2 will be eliminating water. So now both will get condensed. Let me write that compound. CH3 CH double bond C O CH3 O C2H5. Okay, this condensed product, or the condensation product, let me write it as B. Okay, this one I call it as B. So now what we do, now will both A and B will react, and it is going to form the products. Okay, so can I start from there? Yeah, here. This is about step 1, step 2. I think just let me have all the steps on the board, because we can easily get it later. So if I come to the step 3, so here A and B are reacting. Okay, so let me write that one. So A here, so I will take from here. First we'll take the COO C2H5, this whole COO C2H5, COO C2H5 ester group, which is attached to the CH. So CH double bond C NH2 and CH3. Okay, this is A, right? A. Now it is treated with B, this compound. Okay, so here here also I'll take that ester, this group here. Okay, COO C2H5, this whole group is attached to a carbon. This carbon is attached to a ketonic group. So let me take that ketonic group COCH3, and this carbon is with the double bond with this derivative, ethyl derivative. So double bond carbon, here we have an hydrogen, and this is linked with CH3. Okay, CH3, yes. Okay, this is B. See, COO ester group COOC2H5, that is linked to carbon, that is linked to double bond with the CH3, CH3, and below COCH3. Okay, this is B. So now here the nitrogen is the 3 bonds have a lone pair of electrons. The reaction will start from here now. So this nitrogen will give its electron to the next bond. It becomes a double bond, and here the electron density and this carbon increases now. So that's why this carbon increases. So that's why it will be attacking the carbon of the next bond. So now this carbon has got that electrons. So electron density and this carbon increases. So this carbon increases. That's why this will give electron. So this carbon, now this electron density and this carbon increases. Carbon, as you know, electron cannot be held by the carbon. So that's why it will shift to the oxygen. Okay. So now we get this product. Let me write that compound, and the both will get now condensed. Both the compound will become one compound. COO C2H5 CH here. Here it becomes single bond C double bond NH2. So 4 bond for NH, that's why it gets the positive charge CH3. Okay, and this CH will attached with another CH that is linked with CH3. So it is linked now with a single bond to carbon. Here it is ester group COO C2H5. Now it became a double bond carbon oxygen with minus charge and CH3. This is what happened here. Okay, so here nitrogen is having positive charge. So as you already know, nitrogen cannot hold that positive charge because it is an one of the most electronegative element. That's why this oxygen will give back these electrons, and electron density and this carbon increases. That's why these pi electrons will abstract this proton. So when these electrons will be given and the proton has been taken, so this electrons will have been abstracted the proton, so it becomes double bond now. So the electron density and this carbon increases, so that's why these give back those electron to the nitrogen. Okay, the first oxygen minus charge will give an electron, it becomes double bond, so electron density and this carbon increases. That's why the pi electrons will abstract this hydrogen, so this hydrogen will shift to the this carbon. Okay, to this carbon hydrogen will come and this become a double bond, and this electron get back to the nitrogen. Okay, so let me write that structure. Okay, COO C2H5. This becomes carbon only now. A proton has been abstracted by the another pi bond. CH3. This is C. Here an H has been come. Okay, COO C2H5. This become double bond carbon NH3. Okay, again it gets this lone pair CH3. Here now it becomes single bond oxygen. It again become double bond and CH3. CH3. Okay, now cyclization takes place. Okay, now there is a cyclization. So this is not cyclic now, it is going to form a cyclic structures. So these lone pair of electrons will now take this carbon atom. So this carbon is having a delta positive because it is attached to link to the most electronegative element like oxygen. So when these electrons are attack this carbon, these electrons will shift back to the hydrogen, but not easily these electrons are going. So one of the hydrogen has to be eliminated. So it will be start with the hydrogen. So this hydrogen has been given electron to the nitrogen. So then electron density on the nitrogen increases. Hence those electrons will shift it to this electropositive. So are the electron deficient carbon, and these electrons will shift to the oxygen. So and this proton will be shift to the this oxygen now. This become OH. Okay. So from hydrogen has been shifted, proton shifted from nitrogen to oxygen. Okay. So let me write that structure. CH3, C. Here there is an H. Yeah, sorry, I forgot H. This is CH, COO, C2H5. It is single bond. Here it's single bond carbon. Here COO, C2H5. This is a double bond carbon. This NH, okay, is going to form a bond with this carbon, and here this oxygen become OH along with CH3. Now also our nitrogen is having 3 bonds, so that's why it is lone pair has been given. So both now nitrogen is also become stabilized. So now there is a elimination of water molecule, we'll see. So this hydrogen will give its electron as eliminated as proton, and electron density on this carbon increases, that's why it eliminates this OH molecule. So then it is the, here there is CH3, sorry. So hydrogen is proton elimination with the elimination of hydroxide, both will eliminate as water. Okay, so let me write the remaining part. CH3, CH, C, COO, C2H5. This hydrogen has been removed, so see this become double bond. Oxygen is also removed, only CH3 is retained, so it is single bond NH. Okay, from here carbon, here also COO, C2H5 and ester group. Here it is double bond and bond, and this carbon is with CH3. Okay, this is nothing but our first product, that is dihydropyridine derivative. Yes, this is the dihydropyridine derivative. Okay, as further you already know, this dihydropyridine derivative will undergo oxidation with nitric acid, which will give us pyridine derivative. Okay, let me write that one. Yeah, so now this compound will be undergoing oxidation with NH3. So oxidation means here this hydrogen and this hydrogen has been eliminating. Okay, that dehydrogenation is also known as oxidation. So now this hydrogen will give electron, so it become double bond, electron density, and this carbon increases. That's why these electrons will be given to the this bond, and this become a double bond. And of this hydrogen, okay, this hydrogen will be eliminating with this electrons. Have a come in ulta manner. Yeah, so both same. This hydrogen will give electron, this will shift here. Yeah, though both. Okay, okay, fine, okay, sorry. So one of this hydrogen will give electron, it becomes double bond, the electron density and this carbon increases, it gives to the nitrogen, and this further this hydrogen will be eliminating. Okay, okay, somehow it is dehydrogenation. Yeah, C, CH3, C, C, N, C, C, N. Okay, this become double bond, this become double bond, this is also double bond, pyridine ring has been come. Here we have an ester group, here we have a methyl group, here also we have a methyl group, here we have an ethyl ester group. Okay, this is the pyridine derivative. This is actually the product, pyridine derivative. But further we can remove these ester groups by hydrolysis and decarboxylation. So let me write that also. So first it undergoes hydrolysis, and second one it undergoes decarboxylation. Decarboxylation. Okay, now it is going to form a trimethyl pyridine compound. CH3, C, C, H, it become double bond, C, CH3, here nitrogen, a double bond, C, CH3, single bond. Okay, here double bond. Both are same, giving the same product. Okay, here it is a double bond, carbon, hydrogen, oh, bond. You know, in the hydrolysis, these esters will be eliminating as carboxylic acid and alcohol. Okay, and in the decarboxylation, there is a removal of the CO2. Only hydrogen is retained. That hydrogen I have written on this board. So now it is the pyridine. So that pyridine name is 2, 4, 6 trimethyl pyridine. This is the product we can get from the Hans method of synthesis for the pyridine derivative. Okay, this is how this reaction or the synthesis would happen. Okay, so we can classify this into 3 steps. In the first step, the enolic form of the EAA, beta ketoester, will condense with ammonia and forming a intermediate A. Okay, and the aldehyde will condense with this ketone, that is beta ketoester, and forming an intermediate B. Both intermediate A and both B will react. So there is a here the nitrogen has given electron, and these electrons shift to the carbon, and further electron shift to the oxygen. Okay, and the oxygen give back that electron, and this pi electrons abstract this proton. Here nitrogen has got a positive charge, that's why it has happened. So further the cyclization has to take place, because this is not, two compounds has to get cyclized. So here this hydrogen has given electron, and there is cyclization takes place. This hydrogen is shifted from nitrogen to oxygen, that is internal proton transfer. So this we get. Okay, here there is a removal of this water molecule, will give us a dihydro derivative of the pyridine, and this dihydro derivative of the pyridine has an extra hydrogen at the nitrogen and the carbon number 4 that has to removed, and that forming a complete aromatic cycle, and that will be the pyridine derivative by the dehydrogenation or the oxidation. Okay, this product is enough to write, and here we can also remove esters easily. So methyl group removal is difficult because demethylation we don't have any process, so that's why we can remove these esters by hydrolysis and decarboxylation. When we remove esters by, when hydrolysis takes place, these esters will convert into alcohol, will be eliminating, and this will become a carboxylic acid group. And by the decarboxylation, this CO, there is elimination of CO2, hence it will forming an any hydrocarbon, that is forming a pyridine derivative. So here there is elimination of 2 molecules of C2H5OH ethanol, and also 2 carbon dioxide. So that you can write or not, it is depends. Okay, this is how the process takes place. I hope you understand, and for this mechanism you only need to practice. You write it for 2-3 times, then it will be the very simple mechanism it is, but it has a long many steps. Okay, the steps are more, but the process is very simple. Okay, this is one of the synthesis for the pyridine, that is by the Hans, a German chemist. So I think you got it. Please write it, and then you take it down. So if you practice only, then it will be yes, as practice makes man perfect. So you need to practice, write this procedure, this mechanism. Then only you can get it. Okay. Thank you for watching videos, and please like it and subscribe to my channel and share with your friends. Do not forget. Thank you. You can take the screenshot. Thank you. Hi students. Today in this session we are discussing about the some properties, physical and chemical properties of the heterocyclic compounds. So please like my videos and share with your friends, and also subscribe to my channel, because I'm not telling it in the beginning of the every classes, because I just don't want you to distract from the topics. So please do it. Thank you. And when it comes to the properties, so first we'll discuss about the pyrrole molecule. When it comes to the pyrrole compound, if you see its physical properties, physical properties, so it is a colorless liquid. It is a colorless liquid, and if you see its solubility, it is sparingly soluble in water also. A partial solubility we can see in water, sparingly soluble in water, and as it is also organic aromatic compound, it is readily soluble in organic solvent. Readily soluble in organic solvents. Okay, next, if you see its odor, it is usually have a odor like chloroform. It shows chloroform like odor. Almost all these compounds show chloroform like odor. Even furan also show the same kind of odor. And when it comes to the, as it is a liquid, if you see its boiling point, it is around 131, 129 to 131, or approximately 130 degree centigrade, which is usually one of the higher boiling point for this compound. It is not volatile like furan. Furan is having very less boiling point. So especially because it shows some hydrogen bonding also. So that is why it is having little high boiling point. And it turns, though it is colorless, it turns brown, turns brown in air. In presence of air, it turns into brown. So it shows little oxidation in presence of air. So this is about the physical properties of the uh, pyrrole. When it comes to the chemical properties of pure pyrrole, so pyrrole is usually a very weak base, so it shows some reactions of base also, and also it little bit it also act as acid also because it has a higher proton. So it also shows some properties, very weak base and also very weak acid. It shows some amphoteric nature also, and it also undergoes that reduction reactions, oxidations, and some name reactions also. But the very important reaction that is usually asked for 5 marks in your exams is electrophilic substitution reactions of pyrrole, and you also have the same for furan and also for pyridine, which is very important for your exam. For 5 marks it will be as your exam, and now it is NEP in 4 marks. So let us see the only this reaction, electrophilic substitution reactions in pyrrole now. So if you see pyrrole, so here you could see the hydrogen atoms. So these hydrogen only have to be replaced with the electrophile. Okay. So if you see, consider this is a position 1, 2nd, 3rd, 4th, 5th. Okay. 2nd and 5th as usual, the both are equivalent. Equivalent are same. If the reaction takes place at 2nd or 5th, the both are same. As the same for 3rd and 4th position, as these are also equivalent. So we'll get only 2nd and 3rd positions for the electrophilic substitution reaction. So now we have to find out which position, whether 2nd position or 3rd position is more reactive towards the electrophilic substitution reaction. So which gives the more stable compound, then that is the most priority group or position for the electrophilic substitution reaction. As you know, the here one of the hydrogen has to remove or replaced by the upcoming electrophile. So now let us see the positions, whether 2nd position is more gets the more priority or the 3rd position. Electrophilic attack at 2nd position, at 2nd position. So you know, usually in electrophilic substitution reaction there are 3 steps. The first step is the formation of electrophile. The second step is that electrophile attacks the aromatic compound and it forms a carbocation intermediate, and finally the deprotonation or the removal of that H plus takes place. So it usually having 3 steps in the mechanism. So when you see, this is the pyrrole, when electrophile, okay, attacks at second position. Okay, this electrophile attacks at second position. Let's see here. So this becomes single bond now. Here we got the positive charge. Already there is an H. Here the electrophile come and attack. There is also one hydrogen. So this carbocation has been formed. Okay, this actually is unstable. So that's why I'm writing it in a bracket. And this shows the resonance. This shows the resonance. So these electron will shift here. Okay, when these electron shifts, it gives us this resonance structure. So the positive charge comes here, not here. The positive charge come at this carbon. So when positive charge come at this carbon, this show again one more resonance structure. So this will give electron. Now see, now here the nitrogen has given its electron, so it becomes a double bond. So when nitrogen gives electron, it forms 4 bond around it. So nitrogen gets the positive charge. So again, it has to, the reverse will takes place. That's why these 3 resonance structures will be formed during the when electrophile attacks the pyrrole. So now, so obviously at the final step, this proton will be removing. With the removal of that proton, it forms a this compound. Yes, this electrophilic substituted product. So this is about the when electrophile attacks at the second position. Okay, these 3 are the resonance structures of the carbocation formed during the reactions. Resonance structures. Okay, so when this electrophilic attack takes place at third position, electrophilic attack at third position, or it is also equivalent to fifth position, sorry, fourth position. Third and fourth are equal, second and fifth are equal. Okay, so now let us see when electrophile attacks at the third position. So the electrophile is there. So it has been attacked to the pyrrole now. Yeah, when electrophile attacks here, so there is electrophile attacks here, and there is hydrogen. Here also one hydrogen, but here only 3 bonds. That's why it gets the positive charge. Okay, when it gets positive charge, there's a carbocation which is also unstable intermediate. So that's why I'm writing it in a square bracket. So it shows like it also shows again a resonance structure. So this electron will shift to the this bond, that becomes a double bond. Now we'll have this structure. Double bond, electrophile and hydrogen. This nitrogen gets the positive charge. Nitrogen gets the positive charge. But here this cannot give electron because already around nitrogen we have 4 bonds. If it gives electron, yeah, positive charge will not be going because these also become 5 bonds. 5 bond cannot be possible in nitrogen. So that's why we see only 2 resonance structures. Only 2 resonance structures in the case of when electrophile attacks at the third position. So these 2 are the resonance structures. So finally, here also the same thing. When that proton has been removed, it gives us the electrophile attack at the third position. So electrophile here, yeah, it is two substituted pyrrole. It is three substituted pyrrole. Okay, so this is about the resonance structures we found in the pyrrole when electrophile attacks at the second. So this carbocation, and here also we'll have the carbocation resonance. So by seeing the structure itself, you can say now which is the most preferred attack or position for the electrophilic substitution. Yes, the second position is most or more priority for the electrophilic attack, because here we can see the three resonance structures. Here you can only see two resonance structures. So as you know, more the resonance structure, more is the stability. More is the stability. So that's why in the case of when electrophile attacks at the second position, we can find three resonance structures, but here only two resonance structures. So this carbocation is more stabilized by the resonance, and this carbocation is less stabilized, and among which you can see here, and this one, the third resonance structure, which actually has the positive charge over the nitrogen, which is also unstable. So these two are more stable. So here if you see, this is here also we can see the positive charge over the nitrogen, because nitrogen, as it is an highly electronegative element, it cannot hold a positive charge. This only the one of the stabilized resonance structures, and these two are the stabilized resonance structures. So somehow we second position is the shows the more resonance structures, hence the second substituted pyrroles are more commonly found, third is not possible. So that's why the electrophile attacks at the second position is the most priority, is get the so it gets the most priority when electrophile attacks at the second position. So this is usually asked in your exam for 4 marks. Please take it screenshot or note it down. The main important thing you should have to mention after the writing the resonance structure, here we get the three resonance structures, here we get only two resonance structures. So in chemistry, which gets the more resonance structure, that gives the more stable compound. So here with three, so it is the most priority, it gets the most priority, and here it is the less priority. So, and among which you can this is also helpful, because the one of the structure gets the nitrogen, one of the structure in which nitrogen gets the positive charge, here also a positive charge. This is unstable resonance structures. So this is also unstable, this is also unstable. At least you can consider in this case these two, here only one resonance structure, which is a stabilized resonance structure. So that's why usually the electrophilic attack or the electrophilic substitution reactions in pyrrole takes place at the second position. The second position is more priority, gets the more priority than the third position. Now let us see some examples of the electrophilic substitutions, like nitration and halogenation. Students, this pyrrole is more reactive towards electrophilic substitution reactions even than the benzene, because benzene, in case of benzene, we can find only two resonance structures. Here we could have seen three resonance structures, and it shows the more reactive towards the electrophilic substitution reactions than the benzene. So first, for example, we have nitration. So nitration means the electrophile here is the NO2 plus the nitronium ion. Nitronium ion. This nitronium ion will replace the one of the hydrogen or proton in the pyrrole. So here also we got the second position is the most priority, hence the nitration takes place at at second position. So one more thing, as it is a more readily undergoing reactions. So here, so pyrrole readily undergoes nitration also. Okay, so here we take nitric acid instead of sulfuric acid. Usually we take nitrating mixture, the mixture of nitric acid and sulfuric acid. So sulfuric acid, it does not needed here, it is not required because it readily undergoes the electrophilic substitution. Pyrrole readily undergoes electrophilic substitution reaction. That's why I'm taking just a catalyst like acetic anhydride, CH3 CO CH2 CO CH3, acetic anhydride I'm going to take here, not CH2, it is O, acetic anhydride, and HNO3, acetic anhydride. So which is one of the weak compound, but it makes the, because pyrrole itself is a will easily or readily undergoes the electrophilic substitution reaction. This is enough. We do not need a sulfuric acid as a catalyst. So here we got the product. As you know, the second position is the most prior. The nitration takes place at second position. The nitration takes place at second position. So it is 2 nitropyrrole. 2 nitropyrrole. Okay, that one acetic acid, CH3 COOH. Yeah, 2 molecules. So this is, so pyrrole, when it is treated with the nitric acid in presence of acetic anhydride, it easily or readily undergoes nitration, an example of electrophilic substitution reaction, to give us 2-nitropyrrole. This is a byproduct acetic acid. Okay, the same second example, if you see, it undergoes halogenation also. For example, chlorination, if you take, yeah, this is readily undergo, it is readily undergoing in the case of pyrrole. When it comes to the chlorination, okay, when pyrrole is treated with chlorinating reagents like SO2 Cl2, sulfuryl chloride, sulfuryl okay, sulfuryl chloride. Okay, when it is treated with sulfuryl or sulfuryl chloride, it easily undergo electrophilic substitution reaction in presence of ethers, in presence of ether, a solvent. So it readily undergoes this chlorination. Hence, instead of chlorination just taking place at second position, the chlorination occurs at all the positions, irrespective of its priority, whether second or fourth, the chlorination takes place at all the positions. So it is readily undergoing electrophilic substitution reaction. So even this reaction takes place at 0 degree in cold condition also, it easily undergoing this reaction. So if you name this, yeah, 2 3 4 5, okay, tetrachloro tetrachloropyrrole. So this reaction, why I have written, because this shows it cannot undergoing electrophilic substitution reaction just at second position. The second position is the most prior position, but pyrrole is most reactive towards, or the more reactive towards the electrophilic substitution reaction. Hence the electrophilic substitution takes place at all the positions. this actually gives uh, the reactivity, the high reactivity towards the electrophilic substitution reaction of pyrrole. So these two examples are enough for the electrophilic substitution reaction. Thank you. Thank you for watching. Please like my videos, watch it completely, because then only you will get the complete idea of the syllabus or the topics. And please like videos, share with your friends, and also subscribe to my channel. Thank you.